Hello everybody. In the previous video we started with the simplest two states model to derive pricing of financial securities assets, as we call it, and we made use of linear algebra. It was a really gentle way to use a linear algebra in solving this problem. And I'm going to go ahead and now use Microsoft Excel as usual to get the same result, basically. Let me just remind you of the setup. The main question that we addressed was the following question. Given prices of certain financial securities, can we find fair prices of other securities? So in a sense, those given financial securities, we are using them as an anchor to get the other to get the fair prices for other securities. So the answer to that question is yes. Use state contingent claims based on the no arbitrage principle. So here is an example that we used for which we developed an algorithm to ultimately answer the four questions. So basically, two financial securities were given to us: a stock, which is currently priced at $100, and a bond, which is currently priced at $90 today. And as it turns out, the future price for the stock depends on which state of the world we are in the next year, but no one knows. All we know is either state 1 or state 2 will realize in the future, in a year. And if state 1 were to realize, the stock price will go up to $135. And if state 2 were to realize, the stock price would go down to $90. Now, in the case of a bond, which was priced at $90 today, it turns out that irrespective of the state of the world we are in the future, the bond will be valued at $95. So it will earn a $5 profit for its holder, basically. Now, the question then is, how about other securities? If these two securities, Security 1 and Stock 1 and Bond 1, issued by, the stock and bond issued by company ABC, if those securities are rightly priced, based on those prices, can we derive the prices of some other kinds of securities? For example, if I scroll down, remember we asked the question, for instance, how about a bond issued by another company paying $110 in all states at time 1, meaning in the future? So what should be a fair price that should be paid for a bond which pays $110 regardless of the two states we are in? Or here's an alternative problem. Consider yet another stock for another company, again XYZ Corporation, let's say. That stock is paying, we are expecting that stock to pay $65 if state 1 were to realize, and only $40 if state 2 were to realize in that future date. So then the question is, what's a fair price for that stock today? And two other questions related to options, obviously. All right, so the key idea, the algorithm was a two-step algorithm to, given those two securities, stock and bond for company ABC, how do we derive the prices of other financial securities, other stocks and bonds and options? It turns out that the key idea is to first derive the state contingent, the prices of state contingent claims. And this was a new concept for everybody, I guess. So a state contingent claim is a hypothetical security which provides its owner $1 depending on which state happens in the future, and only in that state it gives you the $1, and in all the other state it gives you $0. So $0. So what it means is, as it turns out, using the no arbitrage principle, this gives us an idea of creating a synthetic portfolio which gives exactly the same payoff as stock, as for instance this stock ABC at time 1. For instance, we know that stock ABC at time 1 has a payoff of $135 if state 1 materialize, and only $90 if in state 2. So what we can do is, using these state contingent claims, we can combine a certain amount of those claims, and it turns out that 135 units of state 1 contingent claim and 90 units of state 2 contingent claim would do it. Why? Because the 135 units of state 1 contingent claim, each one paying $1 if state 1 were to happen. So if you purchased 135 of them, each one paying $1, in total, if state 1 were to realize, you would get $135 exactly like the stock is paying. And the same thing for if state 2 were to happen. By purchasing 90 state 2 contingent claims, you get exactly $90 payoff. So this portfolio, consisting of 135 state 1 contingent claims and 90 state 2 contingent claims, replicates the stock security. Does that make sense? So the stock, the value of the stock in year 1, the way it is, this uncertainty can be modeled using these state contingent claims. But wait a second, those state contingent claims, if they have price P1 and P2, it turns out that their combined price today must be such that it should be exactly equal to the $100 if there is no arbitrage opportunities, meaning if no one can make a gain by selling or buying these securities in to beat the system, that must be the case. The two prices should be equal, so no one should try that. And we do pretty much the same thing for the bond. It turns out that because the bond pays $95 regardless of the state we're in, we need exactly 95 units of state 1 contingent claims and 95 units of state 2 contingent claims. And now we manually calculated the solution to this system of equations, and we found out the state contingent claims had the following prices. Now let's use linear algebra matrix operations to calculate prices P1 and P2. These are the prices, the state contingent prices. All right, so all we need is the coefficients of the equation, which is basically 135, 90, and 95 and 95. So that's effectively our coefficient matrix. Let me just move this. Oops. There we go. Let's call it A, and A is equal to. So what we have is A, so all we need is first to take the inverse of it and multiply it with the value vector, which is 190. So A inverse of A is simply equal to, oops, that's the wrong thing, hold on. Maybe I can do, oops, no, that's not my intention, hold on. There you go. All right, so equal to, well, what is it equal to? Wow, how did this equal sign work after all? Yes, let me put this sign over there. Okay, oh, again I messed up. All right, let me just turn this off. Okay, there you go. There, okay. And the inverse of it, hey, we know how to do it, right? So we just select those. Because it's a 2 by 2 matrix, the coefficient matrix, its inverse must be 2 by 2 as well. So I just go to formulas ribbon, math and, finance, right? Actually, no, math, right? So it's under the math section. And we go to the letter M and matrix inverse here. That's it. All I now need is to describe which matrix that I need to take its inverse, and that's this one, and I will just press OK. That's the inverse matrix. Now what I need next is to write out the vector of values for those equations, right? And it turns out that, oops, again I did the same mistake. Let me put this sign. Okay, perfect. So this vector of let me just call it vector because it doesn't show up. All right, there you go. The vector is the left hand side where you have these values, vector values, maybe values. Okay, there you go. And those are 190. All right, so the solution, which is in this case P1 and P2, let me just go ahead and write them. P1 and P2 will be a, because I'm going to ultimately multiply this with this one, the answer will be a 2 by 1. Why? Because this is 2 by 2. This one is 2 by 1. 2 by 2 times 2 by 1 matrix will give you a 2 by 1 again. 2 rows and 1 column. So I can just go ahead and highlight it as well. So it will make more sense. There you go. All right, so that's what we're calculating basically. Oops. Go. There you go. All right, so we will calculate the value of the prices here. And it is just we're just going to do a matrix multiplication, right? MMULT. All I need is to multiply this, the inverse, by this one. That's it. Okay, let me. I think somehow it's assigned to it a name. Huh? Wow, so that's interesting. It called, because it's the inverse, it gave it a special name apparently. Okay, that's good, but you get the idea. And then we're multiplying it with this one, and long behold, we get, there you go, 0.3274, 0.6199. These are the same values that I got by just manually calculating this. That's it. This is just amazing. So we now have the price of state 1 contingent claim, and this one is the price of state 2 contingent claim. And now we are ready to attack and find the answers to all the other problems basically. So it's very straightforward. So the key idea in those all other questions is, all the questions is to basically explain the payoff and somehow combine these state contingent claims according to the payoff of that security at time t equals 1. So for instance, a bond which pays $110 regardless of the state, you can replicate that by simply combining 110 units of state 1 contingent claims, for which each one you are paying this much today, plus 110 units of state 2 contingent claims, and each of these you paid P2. So when you plug in P1 and P2 that we just got over here, 0.32 and 0.61, apparently you get this value. So this must be the value of this bond. That's really good. And you can continue with the stock. The stock promises $65 if state 1 happens, and only $40 if state 2 happens. So 65 state 1 contingent claims plus 40 state 2 contingent claims. Plug in the values for P1 and P2, we get that. And the same way with the options. For instance, in the case of a call option with a strike price of $100, because the strike price is $100 and the stock pays $135 at T1, the call will only be exercised if state 1 happens, and the call will pay $35 in net. And if state 2 happens, because the stock price, the underlying stock, the ABC company stock, will be $90 in state 2. $90 is below the strike price of $100, so as a result the option will not be exercised and I don't need to purchase any state 2 contingent claims. So to replicate that call option, all I need is to purchase 35 state 1 contingent claim and no state 2 contingent claim. Plugging in the value for P1, we get this price. This is a fair price in a sense for this call option with a strike price of $100. So this is the backbone of asset valuation. Obviously, this is just a 2-period model where we have today and 1 year into the future. Now this model can be extended, and our next video will be about that. We can extend it to a situation where either the future state, we can still keep it a 2-period model, but the future state, instead of having only 2 states, state 1, state 2, and state 1 and state 2, now we can include a 3rd state, for instance. So we can add more complexity into the model so that we can better try to understand reality, what we see, the real prices of those securities. Now I want to also provide an anecdotal viewpoint, and it is that even though the for example, in the case of options, the option markets have been in effect since since more than well, I would say probably since the end of the 20th century, and if not earlier. And for almost 100 years, even though those call options or put options, those options were actively traded in the marketplace, traders, investors, they didn't had a clue how to value those securities. But with the framework, with the no arbitrage framework, with the idea of state contingent claims advanced by Gerard Debreu and Kenneth Arrow, I should say, and later on with the groundbreaking work in the case of Black-Scholes option pricing model, the whole thing has been further generalized, and now we have some really good, powerful models to estimate the values of these securities. Obviously, we are not going to go into Black-Scholes model in this course, but for those of you interested, we have derivative contracts and derivatives course under the Master of Financial Analysis program, which if you are an MBA student, or if you are a financial analysis or a business analytics student, you're more than welcome to take those courses at our university. All right, so that's all I have for this one, and looking forward to see you guys for our next video, which will be a two-period model with 3 future states, and how to derive security prices for those for that new setup. Yeah, so that's all we have for now.